Hi, I'm Miles Berry. Not being with you in person, it's impossible for me to know what sort of introduction I've been given. My day job is as subject leader for computing education at the University of Roehampton, where I'm responsible for training the next generation of outstanding primary and soon-to-be secondary school teachers. I do other things too. I recently stepped down as chair of NACE. I serve on the management board of computing at schools and get involved with a few other projects, and would love to be with you in person. I really would, but for one reason or another that's not proven possible today. I hope you've had a great day, I really do, and as I say, wish that I could be there in person, but I hope this isn't going to be too awful, just sat here watching video for the last part of the day. So what I want to talk to you about this afternoon is 1010 reasons for teaching computer science. How long do we have? Actually, it should of course say 1011 reasons for teaching computer science, the 1011th being so that you don't get too worried when you see numbers written in binary. Let's get on with the show. At the start of the week, I tweeted out a link to one of these lovely Google form surveys and said, look, what's your convincing rationale? What's the strongest argument for you for why we should have computer science and programming there on the school's curriculum? And of course one looks through those responses, but the easiest way of analysing data like that is to do a Wordle with it, and these are the words that came up, and it's worth having a look at that. Okay, these 57 responses, no way can I claim that they're scientific or in any way representative of any sort of population other than folks who happened to see the link and had some time to type in a response there, but it is interesting for me to see this focus on programming. That's the word which came up more than any other in these responses. And I think it's worth acknowledging and worth remembering that there is more to computer science than programming. I think we do have that tension there between the craft of coding, an engineering discipline if you will, but actually much, much closer to a craft skill learnt through a process of apprenticeship, of working on alongside the master craftsman and developing your tool set and watching what others do and becoming part of a community of practice through a process of legitimate peripheral participation. And that of course is great fun, it really is. Well, at least for some of it is. And then there's the academic discipline of computer science, part of which you will learn through the craft of programming computers and through having a knowledge of that academic discipline, of the science of computation. I'm sure your coding is going to be an awful lot better, but they aren't the same thing. And yet one typically sees the programming as sitting inside the computer science, but that might be a sort of ivory tower academic perspective on that sort of thing. We all know what the Secretary of State, or rather Michael Wilshaw, thinks about ivory tower academics at the moment. The other thing that's worth looking at, there are a number of other things which are worth looking at on the Wordle here, is this word skills and the word understanding. And I think most of the folk who responded to my survey focused very much on the skills that you develop. And that is, I think, how we've tended to think of ICT in schools for a very large number of years now. This is about developing skills, about ICT capability, if you will, about being able to do stuff with the computer. More and more sophisticated stuff as you get older and older, of course. But it is the way we often teach these lessons is in terms of giving children skills to get things done. And it's easy, of course, to slip into the mode of computer science education is going to be very similar to that. What are you going to do for your lessons? Well, you're going to teach them how to program in Scratch. It's just another cluster of skills there, if you see it in only those terms. And, I don't doubt that I can teach Scratch just as badly as I've always taught PowerPoint. I think there is more to it than that, and there should indeed have been more to our ICT lessons than just skills. And it's this word understanding which I think is the really interesting one. And we'll come back to this in a little while, in a few slides' time. That moving from a position of acquiring a set of skills, of using the technology, to developing an understanding of the technology and of the computation is, I think, where we're heading with this. And I'm personally think that's tremendously exciting, I really do. And of course we have this word thinking in there, and we'll come to computational thinking, I think, in only about 3 slides' time. And look at the word think there too, which is jolly big. And this, these are skills to think with. using the term skills again there, that those who learn to program computers, those who have an understanding of computer science, have a whole new portfolio of tools which they can use to think about problems, to think about reality, and to get things done. And I think that is also tremendously exciting in terms of more motivation for teaching computer science. So yeah, what are my 1010 reasons? Well, let's start with this one. It's fun. And we really ought to try and keep that in our minds as much as we possibly can. That learning to program a computer is absolutely fascinating work. I find it's, well, does it matter what I think it is? Probably not. But I think those who do get stuck into this, those who do persevere with this, find it really very, very fulfilling in all sorts of ways. So, my phrase here is coding is the new gaming. That so much of what it is that gets young people interested in playing computer games applies big time to that process of programming computers, of coding. So, first and foremost, it is fun. It's an enjoyable thing, and there are a number of reasons for that, aren't there? Firstly, you're very, very goal-orientated. When you're playing a computer game, let's just think about the computer game cluster for a start. You're focused on what you're trying to do. There's a clear objective at the end of each level. There's a clear objective to the game as a whole. So you have that sort of goal orientation. You also, I suppose, have that zooming thing. That you're not, yes, there is that overarching objective for the game as a whole, but you've also got those individual objectives for each little level, and within each little mini puzzle that you're trying to solve, or each monster that you're trying to fight, or whatever the game is. Your mileage may vary, I'm sure. There's a high level of interactivity when you're playing computer games, isn't there? That what you do with the mouse, what you do with the keyboard, what you do with the gamepad, or the Wii Fit, or whatever, immediately produces some response from the computer. And alongside that, there's that sense of more to that, of course, you are very much in control of what you're doing in the game. That sense of agency, that sense of action is very apparent in most game environments. There's also, of course, a strong sense of feedback. You know how well it's going. You know whether you're succeeding or not, depending. The dirty little secret of computer gaming, of course, is that it is jolly hard. It is intellectually challenging and thus intellectually stimulating. The children who are playing computer games in your classes, I suspect very often that's one of the hardest things that they're doing. We worry so much, don't we, about setting difficult homework that's going to get them bothered or damage their self-esteem, and yet the children are choosing to play computer games which are so much more challenging than most of the homework which many of us would choose to set. And then, of course, there's this state of flow that Csikszentmihalyi talks about, where you're so utterly absorbed in the thing that you're doing that the rest of time, the rest of everything seems to just disappear into the background. Time seems to fly by. I'm sure that's an experience which all of us in the room, or all of you in the room, will have had when it comes to marking books, don't you think? So, how does that apply when it comes... Let's turn that around and think about this in terms of programming computers rather than just playing computer games. That goal orientation is something which you're very much focused on. You have an overarching ambition of this is what I want my bit of code to do. In order to get to that point, you've got to break the problem down into smaller chunks and solve each of those. So that zooming thing which you get with computer games also applies, I think, to coding. You certainly have a high level of interactivity in the sense of agency and action. You're the one who's typing at the keyboard, or in the context of Scratch, dragging blocks over, or in the context of Kodu, clicking on the buttons, or whatever. That you are very much in control. There's that high level of what I do on the keyboard, etc., determines what the program is going to do. It's my fault if it goes wrong. It's my delight if the thing actually does work. Which brings me, of course, to feedback. And back in the old days, when you were writing your programs on stacks of card, taking those off to be fed into the computer and waiting for the printout of syntax error on card, whatever it was, then you had still feedback then. These days, of course, the feedback is so much more immediate. You can tell immediately whether the thing is working or not. And of course, we have that emphasis on testing and verifiable code when it comes to the proper software engineering side of the game. And of course, challenge this. I mean, yes, yes, it is fun, and I think that's the message I would very much like you to take away from this session. But it is also sometimes maddeningly hard. Let's not be embarrassed about that. John Davitt, describes Scratch, bless him, as being struggleware, and I got a little bothered by this when I first heard him sort of describing, the lovely Scratch as something which you struggle with. But actually, that's its selling point, isn't it? That this isn't something which necessarily comes easily. This is something which you've got to persevere with. If I were with you in person, I'd ask you to put your hand up if you learnt a musical instrument when you were growing up. You're still welcome to do so, but I'm not going to be able to tell who it is who did that. Okay, so why did you do that? Well, possibly because you were interested in music, but possibly because your parents thought it would be a really important thing for you growing up to persevere with something which doesn't come easily to most children. I think coding gives us that too. Similarly with computer games, they're not meant to be easy. And of course, many of us who code, will have that experience of it being an utterly absorbing thing to do, that the rest of reality seems to disappear into the background and time seems to fly by. Other arguments. Douglas Rushkoff, brilliant book called Program or Be Programmed, makes this distinction between those who are in control of the machines, those who take charge of what the machine does, and the rest of society are just going to be, subservient to them and to what their machines have happen. If you think about some of the sort of societal implications for the rapid encroachment of technology in all of our lives, look at the amount of data that somebody like Facebook is amassing, look at the amount of data that somebody like Google is building up about you. Look at all of the information there about me on my Twitter feed. I don't mind that. I'm making a conscious choice, or at least it seems to me that I'm making a conscious choice. But surely, we need to make that sort of rational choice, being fully aware of all of the implications, and an understanding of the technology as part and parcel of that. The illustration which you see here is taken from a book published back in 1980, Seymour Pappert's seminal text called Mindstorms, about putting computers into the hands of children in a very different way from what was happening back in his day, and perhaps still is, if you'll allow me to quote from it. In many schools today, and remember this was back in 1980, in many schools today, the phrase computer-aided instruction means making the computer teach the child. One might say that the computer is being used to program the child. I wonder how much of that is still true. I love the sort of athletics, education, city stuff, but isn't that exactly the same as what Papert was writing about then? Computer-aided instructions, the computer teaching the child. In his vision, he writes, in my vision, the child programs the computer, and in doing so both acquires a sense of mastery over a piece of the most modern and powerful technology, and establishes an intimate contact with some of the deepest ideas from science, from mathematics, and from the art of intellectual model building. So it's not that way round of the computer programming the child. It's t'other way round of the child in charge of the machine, and through that developing this mastery of the technology. And that's something which I think we ought to be aspiring to for the children in our care. But more than that, it provides this insight into the fundamentals of reality, that by programming a computer you come to understand how the world works. Think of it, if you will, as putting the building blocks into the hands of a young child. It's not so that they become architects or civil engineers or construction workers. It's so that they come to understand how reality works, things like conservation of mass, conservation of volume, gravity works downwards, some structures are more stable than others. These are fundamental things which, putting the right toys and the right opportunities in the way of a child, allows them to understand. Why does this matter? Well, because you start thinking about the world differently. One of the things you'll hear about as you get more involved with this computer science on the curriculum business is this notion of computational thinking, and I think we have elements of that in the programme of study as you now see it. That there's more to this than learning about how computers work, and there's more to this than learning how to program computers. These things are a means to another end. And that's giving children a whole new set of tools with which to think. So when computer scientists or programmers look at problems, they look at them in a peculiar, or at least particular, sort of way. You have this notion of decomposition, that you look at the pizza which you see on the screen in front of you, all being well, and you think, pizza, no. You think, what is that made of? What are the things that form that pizza? And of course we have the base there, and we've got cheese there, and we've got salami there, and olives. Oh, and are they raisins? Oh no, that must be anchovies. I don't know, it's hard to tell this close up to the screen. So you have those component parts. This comes back to what I was saying earlier about the coding and gaming thing. When you have a problem in front of you, we break it down into the smaller parts and tackle each of those problems separately. So how do you make a pizza? Well, you've got to get all of those ingredients together first, and each of those ingredients might set you in some particular challenge, although we tend to go to Sainsbury's or wherever and just buy the thing. The notion of abstraction, that we don't worry too much about the level of the detail. Think, if you will, about the whole planning process. The Secretary of State, bless him, is not interested in your lesson plans. He's interested in a very abstract model of the curriculum, that there should be these subjects on it. And perhaps on a good day he's interested in what goes into the programmes of study thing for each of those. But he's not going to pay any attention at all to what one school puts onto their scheme of work. That's something which happens at a far lower level of abstraction. That he's only interested in the sort of high level language there. And indeed, I suspect many a head teacher isn't particularly interested in individual lesson plans, much as they might want you to think that they are. Your medium term plan, yes, the scheme of work for the subject in the school, but the actual what you're doing on a Tuesday afternoon, that's kind of your responsibility to deal with that sort of low-level code. And of course you've got a similar sort of thing going on with the pizza there. Most of us, when we're eating pizza, just sort of go and order pizza. That's our approach to solving that problem. There are ways of crossing the abstraction boundary there and dealing with the individual ingredients. And you might go and buy the base and buy the ingredients. Or you might cross a further abstraction boundary and think about, okay, how do I go about making the base there? But most of the time we're interested in the sort of the higher level black box or pizza box components there, and not worried too much about the level of detail, which other people can solve those problems for us. We think in terms of a system there. Sorry, pattern. Again, I've never worked in Pizza Express, but my suspicion is that the recipe book in Pizza Express, broadly speaking, looks along the following lines. Get the base of the pizza, get the cheese, get the tomato sauce. Get the cheese, get the topping, and put those together, put it in the oven, and there's your pizza. You have one standard pattern for all pizzas, of which we just vary, what the base looks like and what the topping looks like, to produce lots and lots of different pizzas. And again, the computational thinking approach tackles the whole class of problems rather than tackling problems individually. And then, of course, we have algorithm. The classic example of illustrating an algorithm, certainly when you're thinking in terms of primary education, is the notion of the recipe, of the step-by-step instructions that you follow. And I've just given you an example for how you might do that for pizza. I'm sure Phil would be only too happy to sort of act as a robot baking pizza if anybody were to ask him to at the end of the session. So you have there this sort of step-by-step approach to solving problems. And you can get more and more sophisticated examples, I'm sure, of pizza recipes going on there. One of the things worth saying here is, once you've got that kit of techniques, the decomposition, the abstraction, the patterns, and the algorithms, then that's something you can apply across the whole of the curriculum. There are obvious applications of this in maths education, but you'll see it also in design and technology. You'll see some of this also in music if you start looking for it. You'll see some of this in early language work. Think how many young children's songs are based on a sort of algorithmic approach where you have a pattern into which certain things start to fit. You'll also, I think, start seeing this at whole school level. And I gave you the example of abstraction when it came to planning. But, the algorithmic approach, what's the most efficient way of getting this particular task done, is something which computer scientists and those who program are uniquely, I think, gifted at seeing. More examples from school. This is, for me, the winning argument. I love the other arguments, don't get me wrong, but this is the one that makes the convincing case as far as I'm concerned. That digital technology has become such an important part of our lives, all of our lives now, as Jim Rose put it, as something which is essential for learning and life. That to describe yourself as educated in the third millennium and not have an understanding of how this stuff works is, to me at least, an empty claim. It's not about getting a job in the industry. It's not about being able to do this stuff later in life. Lovely as these things are, important as these things are, it's about what constitutes an education. There are plenty. You're going to find yourself, I'm sure, or you find yourself teaching painting to a whole class of children all at the same time. You're going to find yourself doing the sort of thing which is on the picture in front of you there, of having children making music themselves. And you're also going to have children writing poetry themselves. Very few of the children in your class will become professional artists. Very few of them will become professional musicians. A vanishingly small number are going to become professional poets. Yet the fact that they don't go off and get jobs in these industries is no reason not to teach these things. We teach these things because that is part of what being educated, and at least primary education, includes all of these lovely things. This is about a liberal education, about being a rounded human being, about having an appreciation of a whole variety of pursuits for their own sake, not just because you could get a job in this area. It's not a vocational thing. It's about understanding. It's about having a rounded education. I'm starting to repeat myself here, aren't I? That said, it's probably a lot more useful than, dare I say it, I'm just, again, don't have the benefit of seeing who's there in the room with you. But, in terms of utility, it's probably a lot more useful than things like art and music and poetry. I don't know, they have their place, they really do. But we don't do them because they're useful, we do them because they're interesting and important, and ditto computer science, ditto programming. We do these things not because they're not merely because they're useful, but because they're interesting. They are also useful, though. Computer science is certainly very useful. And I'm not thinking here merely about going and getting a job as a programmer or a software developer. It's jolly useful to be able to write code in a whole host of different ways of life or forms of activity. Yeah? In higher education, physics degrees, biology degrees, all of the sciences, all of engineering, mathematics, statistics are going to require the ability to write at least some code. You're starting to see all of that sort of digital, computerized, algorithmic approach taking hold in other domains too, even within the field of education. The ability to be able to write code which analyzes huge sets of data is going to set somebody apart when it comes to academic research. It really is. And, in similar domains too, there's a lovely movement there about the digital humanities. I'm thinking and talking at the moment in terms of higher education. But of course, the same is going to be true in a whole host of careers too. The illustration there on the slide of the City of London, and think how that has been transformed in the last, I don't know, what is it going to be, about 20 years? In terms of the algorithms taking control of how the stock exchange works. Those who are really successful in the city these days are not those who happen to have been at school, the right sort of school or whatever. It's those who can program computers, the quants as they're described in the city, those who can write the algorithms, write the software for the computer to go off and make all of those trades. And that's just one example. The same is going to be true in a whole host of different professions and other spheres of activity. Think about how important algorithms are and a programmatic and algorithmic approach is to some of the more creative domains of life. Think about that in terms of music. Think about that also in terms of art. Okay, not all music, thankfully, but it is starting to make a difference there. Okay, so yes, it's important for a whole host of careers, and it's also really important for those in a management position, those who are buying IT stuff or making decisions about information technology can make far better decisions if they've got an understanding of how that software, how that technology works. It is also, though, really important that we do have people working in the industry in this country. Eric Schmidt in the McTaggart lecture in Edinburgh, which came the summer before Gove's speech at BET, talks about us throwing away our great computing heritage. And yes, the UK have been pioneers in so much of this. If you think back to folks like Charles Babbage and Alan Turing and Tim Berners-Lee and Steve Ferber and the rest of the ARM team, we have absolutely pioneered so much of this. And I think many would argue that it'd be absolutely important that we continue to build on that success. The illustration there, Little Big Planet, is that it's used as the cover for the Next Gen report. Ian Livingstone and Alex Hope being asked by Ed Vasey at DCMS about what can be done to return the UK visual effects industry and the UK games industry right to its prominence at the top of the league tables worldwide. And their number one recommendation was get computer science onto the curriculum as a statutory entitlement, because unless the pipeline is addressed, then where are their new programmers going to come from? Ian Livingstone, interestingly, takes very much a sort of practical coding line to this. He's not so much interested in having lots of academic computer scientists, much more interested in having folks who can write code. And of course, both are going to be important. Let's deal with the academic computer science thing. You probably have heard that computer science, at least from AQA and OCR, is now on the English baccalaureate list of approved subjects, and they describe it there as being as the fourth science. To my mind, it's actually the zeroth science, in that it is far more fundamental than the other three. If you'll allow me, what is computer science? What sets it apart as a science? What's it about? And it is about what is computable. It's the science of understanding what can be computed and how that might be done most efficiently, most effectively. Peter Bentley, writing a brilliant book called Digitized. If you get a chance, do download a copy or buy a copy. And whether it's paper or download is up to you. So get on with it, Mars. Right. Says the Turing machine, of which you see somebody who's actually built one of these things, the Turing machine is still one of our best theoretical tools for understanding what can and cannot be computed. I think ideas of computability are stronger than many physical laws. You can get down to the foundations of what is and what isn't computable. They're fundamental categories of reality. I think they're built into our universe and any possible conceivable universe. That's an amazing thought when you think about it. More fundamental than fundamental physics is what is computable. Think about that in terms of information. There's one way of thinking about reality as a system to convey information. I'm not sure whether that's helpful or not. And Bentley goes on to talk about the three types of problems. There are things which is easy to solve, and they're the sorts of things which we set to children in school, of course. And there are things which it is actually provably impossible to solve. And that's, some of Turing's great insight, is that there are whole classes of problems which you can never solve, which is impossible to determine. And then there are things which are really hard to solve, and that's where the interesting territory lies for computer scientists. Can these things be is there a better way of solving problems which at the moment look as though it would take forever and a couple of days in order to solve? If we could find a better way of solving them, then a whole other things open up. So as I said earlier, it isn't about skills, it is about an understanding of how the technology works, of how computation works, of what is computable. So as you're going back into class on Monday and teaching ICT lessons or teaching computing lessons or teaching whatever lessons, don't try and move away from I'm going to teach the children how to do this to I'm going to teach the children how this works or what's happening when they do this. My favourite example of this is about the internet, and indeed about Google. And this may have been something which you've talked about already today, but we ask, allow me to sort of slip into an anecdote about Roehampton. When the students come to us, we get them to fill in an audit, and they do jolly well when it comes to their skills. Really very impressive scores. 2/3 of them proficient, competent, proficient or expert across a whole host of 18 skills. We also now ask them to grade themselves in terms of their knowledge and their understanding. And the figure for understanding is so much lower. If memory serves, I don't have the figures in front of me. It's like a quarter of our students grading themselves as competent, proficient or expert when it comes to an understanding of how the technology works. And I'd like that to change. Another example, we talked to our year twos about the internet and the web, and I asked them if anybody could explain the difference between the internet and the web. They've all used the internet. You know, the undergraduates many of them are digital natives in the sense that they have been born more recently than the World Wide Web was invented. And I'm lucky in a group of 30 if I get maybe 4 or 5 hands going up, for I can explain the difference between the internet and the web. And, you know, again, if I were with you, I would make you do this now. But, you know, what is that difference? What's the difference between the internet and the web? And how do you explain that to a 7-year-old? Or how do you go back and explain that to one of your colleagues when you return to school on Monday? And again, how does Google work? You know, in terms of skills, we're all pretty good. Okay, other search engines are available. We're all pretty good at finding information on the web. You know, as you say to any child, you have top end of Key Stage 2, go and research about this, they will immediately go to a search engine, and you all know which search engine I mean. But how many of those children will have an understanding of how Google has selected the results which appear on that page and how Google has put those results into order? How does Google determine what goes top of that list? And do you not think that's something which we ought to be teaching? By all means, teach them how to search effectively. The skill does matter, but actually, in terms of thinking about the future, an understanding of how it works is far more important. And I see this not only in terms of computer science, but in terms of critical digital literacy. You know, what's going on there? What are Google doing with all of that information? An understanding of those processes matters. And yeah, that takes me to, you know, point number, I'm trying to do this 1001 in my list here of 1010 reasons for teaching computer science, that we are preparing the children that we're teaching for a future which we cannot guess what it's going to be like. Think about what it was like when you were at primary school. I'm probably now older than most of you in the room, which is bothering me. You know, that when I was at primary school, the sense of the resources to which we had access to in our classroom were a few books and a couple of maps and a few things lent from the museum, and not much more than that. These days, pretty much any primary school classroom in the country, you go in there and you've got access to the whole of the world's knowledge. Well, that bit which has been digitised and put on the web on the 72-inch screen at the front of the room. Better than that, if you've gone down the one-to-one deployment device, if you're allowing children to bring in their own devices or you're providing them with iPads or whatever, each of them can find out pretty much any bit of information. All of those YouTube videos, all of those Wikipedia articles, all of that information. And that's within my lifetime. You know, that's within the last 30 years that we've seen that transformation of learning. Not so much schooling. We still have sort of 30 children and somebody a bit older and wiser at the front, don't we? But that transformation of learning is amazing. And what's that going to be like in 30 years' time? You know, come 2045, when Kurzweil says that, you know, my phone here, or what replaces it in 30 years' time, will have the processing power of the whole of the human race's minds. That's really scary. Okay, I think Kurzweil's exaggerating there. But you know, what's the best way to prepare children for a future like that? It isn't being able to make PowerPoint slides. It really isn't being able to make PowerPoint slides or even stop motion animation, folks. Those skills are going to be something which we'll look back on as quaintly as we do handwriting practice and writing out notes from textbooks. And okay, there's still a place for both of those things, I know. But the sorts of things which I was doing back at primary school many of them seems kind of quaint now, don't they? 30 years' time, those sorts of skills will be long, long gone. The argument for computer science is that this is something which doesn't change as the technology keeps on getting more and more exciting or powerful. So yeah, the understanding of computation, the ability to be able to take control of those machines, is something which will stand us in better stead than just being able to use particular applications. And finally, if you want a 1010th argument, there is one which really ought to clinch the deal for everybody, and it is, I'm afraid, because the Secretary of State says you've got to. Or at least he does if you're in a local authority maintained school. Come 2014, computer science, programming and other aspects of computer science goes on there on the statutory national curriculum. And yeah, we're going to have to do the best that we can with that. We really are. I think, I'm certainly been one of those who've seen this change very positively for the sorts of reasons that I've just given you. It's worth saying, though, that as it stands, the draft programme of study doesn't necessarily embody the breadth and balance which your curriculum by law has to. You have a statutory duty to provide a broad and balanced curriculum. And I think if you just teach what's on the programme of study, that may not necessarily be the case. The computer science stuff is absolutely great, don't get me wrong. You probably wouldn't have thought I thought otherwise after the previous few slides. But I think there has to be more to it than that. So let's make sure that we have the children that you're teaching also creating media in a digital domain. Okay? The national curriculum is merely a minimum entitlement. Again, you have a statutory duty to prepare your pupils for the opportunities and a moral obligation to prepare your pupils for the opportunities, responsibilities and experiences of later life. And that later life can be a very long time these days if advances in medical technology continue. As the Secretary of State says in the introduction to the draft curriculum, there's time and space in the school day, in each week, in each term, in each year, to range way beyond the national curriculum specifications. He doesn't say way. I think it's worth bearing that in mind. Think about your Google 20% time. If you're an engineer working for Google, one day a week you get to work on your projects. Why not put that into practice in school? Yes, do the national curriculum. Yes, teach the computer science. But one day a week, why not have a day when you get to choose what you teach? And one day a week, why not have a day in which your pupils get to choose what they learn? Perhaps using technology, perhaps not. There you go, radical thought with which to end. I'm really sorry that I'm not there in person because I would love to engage in a conversation about this and talk about some of these ideas with you. I hope that's giving you something to think about. But we can have a conversation. There's an email address there. Please do email me if you want to any responses or criticisms of what I've been talking about. I've been talking about. I don't keep my blog particularly up to date, but there is an address there, and I'm on the Twitter thing, so I'll have a look at what the hashtags say. But I'm at mberry if you want to get in touch about any of this, or indeed about anything else. So as I say, I hope you've had a really good day, and I'm sorry I'm not there to be enjoying it with you. But thank you very much for listening.